Hello, students. We have started with our first chapter, charges and fields, and we have discussed almost all the topics of electric charges. And today we will start with so electric field is a positive charge or a negative charge is said to create its field around itself. A positive charge and a negative charge creates a field around itself, and the space around a charge in which a charged particle experience a force is said to have electric field in it. For example, if I say I have a positive charge here and I have another positive charge here, so if this positive charge is repelled by this positive charge, and similarly this positive charge is repelled by this positive charge, we can say that both the positive charges have a field around itself, and that field is known as electric field. So electric field can be defined as the space around a charge in which another charged particle experience force is said to have electric field. Electric field is represented by capital E and it is a vector quantity. The next is electric field intensity. Electric field intensity at any point is defined as the force experienced by a unit positive form. It will be written as E is equal to F upon Q naught. For example, this Q plus Q is a source charge and we have placed a Q naught charge here at so this point in this charge Q naught will experience a force as you can see in the diagram. So electric field intensity at any point is the force experienced by the charge placed at that point. Mathematical form will be E is equal to F upon Q naught, where Q naught tends to 0 so that the presence of this charge may not affect the source charge. Tends to 0. Why? Because the presence of this Q naught charge will not affect the source charge. After the source charge Q naught may not affect the source charge Q, and its electric field is not changed. Therefore, expression for the electric field intensity can be written as E is equal to limit Q naught tends to 0 field intensity. The next SI unit of, I told you, the mathematical form for electric field intensity is E is equal to F upon Q. Here Q is the electric field intensity. So we know the force have a unit Newton and charge has a unit Coulomb. So its unit will be Newton upon it like this, or you can say volt per meter, and this can be written as joule per coulomb meter. And in CGS unit coulomb is charge is stat coulomb, that is why it is written dyne per stat coulomb, and you know dyne is the CGS unit for force. The next is dimensions. We have studied about dimensions. The dimensions of electric field intensity are M, L, T minus 3 and A minus 1. The next is direction of electric field. Electric field intensity E is a vector quantity. Direction, so that is why it is a vector quantity. An electric field due to a positive charge is always from away from the charge, and that due to a negative charge is always towards the charge. Means if I do a positive charge directed away from the electric charge, and for the negative charge, I will draw here for the negative charge. For the negative charge, electric field will be directed towards the negative charge. Hope it is clear. So we can see direction of electric field for a positive charge will be away from the positive charge, and for a negative charge it will be towards the negative charge. It is shown in the diagram also. Here placed a positive charge we can see, and the direction of electric field is away from the positive. Electric field is directed towards this negative charge. The next comes the relation between electric force and electric field. Electric force and electric field. In an electric field, E of a charge Q experience of equal to QE. We have started upon Q, so F will be equal to E into Q. The same it is written here. In the direction of the field, and if the charge is negative, the force act on it in the opposite direction of the field. Now we are talking about the force experienced by the charge and the electric field. So if we are having a positive charge, the force experienced by the positive charge will be in the direction of the electric field, and if we are having a negative charge, so the force will be directed opposite to the direction of the electric field. It is given here in the diagram also. You can see this is the diagram. This one is for positive charge, electric field, force is along the electric field in the same direction, and here this is for the negative charge, the force is opposite to the direction of the electric field. The next comes the superposition principle. Superposition of electric field. We have studied about superposition principle. The resultant electric field at any point is equal to the vector sum of the electric fields at that point. Vector sum of the electric fields, that is E, is equal to E1 plus E2 plus E3 up to so on, and the magnitude of the resultant force diagram. This electric fields, and it will be written as E is equal to under root of E1 square plus E2 square plus 2 E1 E2 cos of theta, and its direction will be given by tangent alpha is equal to E2 sin theta upon E1 plus E2 cos theta. The next comes the continuous charge distribution. Before this, that we are having point charge. What is point charge? Point charge produces its electric field at a point which with distance r from it. Diagram is here. Point charge produces its electric field at a point P. Suppose this is a point charge, we are having capital Q. So it will produce a electric field at point P, and the mathematical form will be EP. EP means the electric field intensity at point P r square, and this r square is the distance the point charge and where the electric field is produced up to that point. So we have started this thing that for positive point charge, electric field intensity E is directed away from it, and for negative charge, electric field is directed towards it. The next comes the continuous charge distribution. Number of ways in which we can distribution over types of charge distribution. So charge per unit length, if we want to distribute charge across the length, so the symbol will be lambda. And if we want to distribute the charge per unit area, symbol is sigma. And for per unit volume, the symbol is rho. So a total charge q is distributed along a line of length L over a surface area A and over a volume V. So we can calculate the charge density. Lambda is the charge density, so lambda will be equal to q upon L. And sigma charge density, sigma is the charge per unit area, so sigma will be equal to q upon A and rho will be equal to q upon V. These are all the charge densities. The next comes the properties of electric field lines. The first property is electric field lines originate from a positive charge and terminate to a negative charge. This you can say very important that electric field lines originate from the positive charge and terminate at the negative charge. The second one says the number of field lines originating or terminating on a charge. The number of the field lines which are originating from any of the charge or terminating is proportional to the magnitude. Magnitude means 5 coulomb or 6 coulomb or 10 coulomb of the charges. So number of field lines are directly proportional to the magnitude. Next property says area will be proportional to the magnitude of the electric field there. Means the number of field lines passing through the perpendicular unit area will be proportional to the magnitude of the electric field there. Means the number of lines crossing the perpendicular area will be proportional to the magnitude of the electric field. Means how much electric field is there, the number of field lines passing through the perpendicular area will be proportional. The next one is tangent of a field line at any point gives the direction of the electric field to that point. This already you know. If we want to find out the direction of electric field line at any point, we can take the tangent at that point. Diagram is also given. The next one is two or more field lines can never intersect each other. This is another important property of the electric field lines. On this property, this year also in CBSE one question was asked that why two electric field lines can never intersect. So the answer will be two electric field lines never intersect because at one point there will be two directions of electric field lines, and so at one point two directions will be there and it is not possible. Or you can say the another option can be like this: electric field lines originate from the positive charge and goes away from the positive charge and ends at the negative charge. That's why they do not form a closed continuous path. That's why they do not intersect. Means they cannot have multiple directions and uniformly placed. These field lines are straight, parallel and uniform. I've already told the electric field lines do not form a loop. In this diagram also you can see electric field lines are going away from the positive charge and it goes towards the negative charge. They do not form a closed loop. The next property is electric field lines originate and terminate perpendicular to the surface of the conductor. Means electric field lines originate also and terminate perpendicular to the surface of the conductors. It is given. And electric field lines do not exist. The next property is field lines always flow from higher potential to lower potential. In a region electric field is absent, there will be no Hope it is clear. If there will be no electric field lines will not exist. So these were the properties of electric field lines. The next topic we will continue in the next class.